Okay. So welcome back. So first, I will go through the counting method in probability. After that, I will go through the Poisson distribution and the hypothemetric distribution. Then I will go through the tutorial question 1, 2, 3, 4 in tutorial 2. That will be finish all the lectures. And then next week, I will, in tutorial, I will go through the tutorial 4, the hypothesis testing part. So first, we look at the counting method in probability. So we can see this is the fundamental principles for the counting method. The statement is very straightforward. Assume that k operations are to be performed. If there are n1 ways to perform the first operation, and for each of these ways, there are n2 ways to perform the second one, and the total number of ways to perform the sequence will be the product of n1, n2 up to nk. So I changed the example a little bit. In the old example, that's assembling a computer. And here, I just changed it to order a meal. So if we go to a restaurant, and this restaurant provides 4 choices of salad, 6 choices of drinks, and 8 choices of main dish, and 5 choices of dessert. It sounds we don't have too much choice. But if we want to form a meal, and we need to choose 1 salad, 1 drink, 1 main dish, and 1 dessert, then how many different meals that we can order? So when we change our salad, it's a different meal. When we change our main dish, it's a different meal, right? So even this restaurant only provides this very limited choice. And we can see the ways that we get a meal is around 1,000. So here, the first operation is to choose our salad. The second operation is to choose our drinks. The third operation is to choose our main dish. And the last is to choose our dessert. So after these 4 choices, you can get around 1,000 combinations. So this is the fundamental principle of counting method. In the following slides, we will focus on 2 concepts. One is a permutation, the other is a combination. For the permutation, basically, the order does matter. And for the combination, the order does not matter. So, for example, we can see we need to introduce the simplest permutation first. So this is the number of permutation of n objects. And this is given is equals n factorial. And n factorial is n times n minus 1 times n minus 2 up to 1. So we can see the smallest number is 1. So if we get the factorial of 0, we just define whenever you get a factorial of 0, it equals 1. For all others, you can calculate it by this formula. And n must be an integer. So we can see how many often you guys go to the theater or go to the cinema. And in Singapore, when you buy the movie ticket, you need to choose your seat at the same time, right? That means if you are first one to buy the movie ticket, you have all the choice. And if you are second one, then at least 1 seat you cannot choose, right? So then we can see if we get 5 people standing in a line at a movie theater, how many different orders can they be arranged? The order here, that means if we get A, B, C, D, E, 5 people, and A, B, C, D, E is one order, E, D, C, B, A is another order, right? So how many orders that they can arrange? So if you are A, then you are first one, or you are second one, or you are fifth one. Is the same or different? Different, because if you are first one, you can choose any seat that you want, right? If you are fifth one, the first 4 people already choose their seats. That 4 seats will not available for you. So this, in this question, the order does matters. So this is a permutation problem. So we need to use this is n factorial. N equals 5. So n factorial is 5 times 4 times 3 times 2 times 1 equals 120. Do you guys like this panda? Anyway, so then we can see if we choose k objects instead of n objects from n objects. So this time, we don't need to arrange all the objects. We just arrange part of objects. Then the number of permutation equals n factorial divided by n minus k factorial. Can you understand this part? So n factorial is just like a previous slide. That is the number of ways we have for n object. And now we only choose k objects out. And the order of this k object matters, right? That how many objects left? In total, we have n objects. Now I choose k objects out. How many objects do we left? N minus k, right? For this left n minus k object, the order doesn't matter, right? How many ways do they have? N minus k factorial, right? So we need to divide by this because for this part, n minus k objects, their order or not doesn't matter. So for example, this one is boring. So we can come back to the buying movie ticket. And then now we have 7 people. 7 people, only 5 of them will buy the movie ticket, right? So then we can arrange these 7 people. We can choose the first 5 out, right? Arrange these 7 people, that's n factorial, is 7 factorial. And choose this 5 out. These 5 people, the order of for these 5 people doesn't matter, right? Because they will get the different seat availability. And for the rest 2, we get F and G. No matter it's FG or GF, will this affect the arrange for the first 5 people? No, right? So then we need to divide all the possibility for the rest of the people. So that's n minus k factorial. Then back to this example, they said 5 lifeguards are available for duty one Saturday afternoon, and there are 3 lifeguard stations. So basically, we just need to choose 3 people out of 5, right? And these 3 people will assign to different lifeguard station. So the order for these 3 people matters. So this is a permutation problem, and we choose 3 out of 5. So we can plug in this formula and get a 5 factorial this and 2 factorial this, then it equals 60. So you need to, here the order matters because the 3 lifeguard positions are different, right? If you are in swimming pool 1, the position 1, or you are in station 2, they're different. Maybe station 1 just right under the sun, nobody want to be there, right? Any questions? Or still not recovered from New Year mode? Or Valentine's mode? Either one. Anyway, so then we look at the combination. For the combination, I said the difference is, in this case, the order doesn't matter. So in this case, the number of combination of k objects chose from a group of n objects is n factorial divided by k factorial divided by n minus k factorial, and denote as n over k. So back to the previous example, when the rest doesn't matter, we divide by n minus k factorial. If the previous part also doesn't matter, then we divide by k factorial, right? So we just don't want to repeat counting certain combination. In this case, no matter A, B, C, D, E, or E, D, C, B, A, they are same because the order doesn't matter in this case. So we need to divide by another factorial, k factorial. And here, no matter, because this is long, so people get the short writing about this, it write this way. No matter you see this parenthesis n, k, you can replace it by this one. These 2 notations are equivalent, and we will use this notation in hypergeometric distribution. So when you go to the hypergeometric distribution, so this notation, you should come back to this slide 5 and replace it by this one. Okay, so this one, example 4, is at a certain event, 30 people attend, and 5 will choose at a random to receive door prize. And here, all the price are same. It's just a $20 voucher. So no matter you are first one or the 5th one, you get the same thing, right? So in this case, the order doesn't matter. We just choose 5 people out of 30. No matter you are first one or 5th one, as far as you are chosen, you get the same price. So in this case, this is a combination problem. So we can plug in this formula, n factorial divided by k factorial divided by n minus k factorial, and plus numbers and get this. Okay, straightforward. Then we can extend, for this case, basically we divide the n objects into 2 groups. One include k objects, the other include n minus k objects, right? And we can divide it into more groups. If we divide it into more groups, any exchange inside a same group will be same. So we will extend it to n factorial divided by k1. k1 is the number in the first group. k2 is the number in the second group. So we get n factorial divided by k1 factorial, k2 factorial until kr factorial. Okay? So this is a die. It should be a dice, not a die. This is a typo. Nobody want to die. So we get this. Then we can see 3 of them come up to 1, 5 come to 2, 4 come to 3, 2 come to 4, 3 come to 5, and 3 come to 6. And how many different arrangement of these outcomes are there? So in this way, we don't care about the first dice, the first time it come to 1, or the second time it come to 1. As far as in total we have 3 times is 1 is okay. So this is a combination problem, and basically we divide it into 6 groups, and we can see we get the n factorial. Here is 20 divided by 3, 5, 4, 2, 3, 4. This is 6 numbers. So this is 6 groups. So we get the answer is this one. Okay? Any questions? So the summary for this part is first the fundamental principle of counting is just if we have n operations and the combination of this is n1 times n2 times until nk. And this is a permutation and this is a combination. And do remember when you see this symbol, just replace it by this expression, then do the calculation. So we have one bonus, the clicker question. And this time, not use a clicker, you use your cell phone. So you can text your friend. They can do it remotely. Okay, I need to connect. Okay, so this is the question. Just apply the knowledge that we learned before. There's something wrong. Let's see. Anyway, so the question is here, and our high-tech run into problem again. I reset it and use the preference, apply all, then start. Did you see this part? It flash very quick, then the toolbar just flashed very quick, then disappeared. I don't know why it is. Anyway, you can look at this one. We don't need the figure. So this is the question. For a class of 50 students, what is the probability that at least 2 people have the same birthday? A, smaller or equals than 25. B, between 25 and 50. C, between 50 to 75. D, between 75 to 100. So the session ID is 860372. Let's see if I can get a response without the toolbar. Ready? So you can key in your answer. I don't know if I can record it. Doesn't work? Okay, then we come back to the most reliable way. How many people choose A? Raise your hand. 1, 2, 3, 4, 7, 8. How many people choose B? B. How many people choose C? How many people choose D? 1. Okay, I only get 9 people have a response. Don't be shy. I cannot memorize everyone. How many people choose A? Now it becomes 7. Okay, how many people choose B? 1. How many people choose C? Nobody. How many people choose D? 1, 2, 3. Okay, majority is choose A, right? So we just feel the probability will be very low. Is that true? The probability that we find 2 people have the same birthday among 50 students is 97%. So you can see don't ignore this boring lecture. It can help you get these surprise results. So don't be surprised, and I will prove it mathematically first. Then, now we get enough students in the classroom, and just show you in our lecture room how it is true. Okay. First thing, we need to make assumptions. The first one, we know in this February, we have 29 days. But normally we don't. So first assumption is I need to exclude 29 of February. Is it okay? Not a big approximation. Then, anybody has twin brothers, twin sisters? Oh, okay, lucky you. You are excluded. Because if we get twin brothers or twin sisters, normally they are born on the same day, right? I cannot guarantee. And so this is the second assumption. The third assumption is can you see it? Oh no? What happened? That one is okay, but this one don't. That's a big problem. Maybe. Okay, it'll come up. So we made two assumptions. One is exclude 29 of February. Second is we exclude that student because we don't want to get twins. And the third one, this one is a little bit equal probability for every day. So the third assumption, it just assume on each day we get the same amount of new babies. This assumption definitely not true. And maybe after 9 months, we get more babies because this weekend is a Valentine's Day. But we don't consider this. We just assume every day is a Valentine's Day, okay? So we get these three assumptions. Then I need to define one function, P of n. This is the probability that the nth person doesn't share his or her birthday with the previous n-1 people. And the previous n-1 people, we also assume they don't have the same birthday, okay? Then we can see what's the probability that we only have one person. Oh, thank you. What's the probability that we only have one person, and this person doesn't share his birthday with Noah? 1, right? And what's the probability that we get the second person, and the second person doesn't share his birthday with the first one? The total days is 365. The first one occupied 1. So the rest is 364. So this person is get 364 over 365 to have the different birthday, right? We assume that every day is equal. The first one just occupy 1. The rest is 364, right? So it equals 364 divided by 635. How about 3? The first 2 persons will occupy 2 days. Then we get this, right? Is everyone with me? Then we can see, in general, if it's a Pn, it's 365 minus the previous n minus 1 divided by 365 equals 366 minus n divided by 365. And what's the probability that all these n people don't have the same birthday? The first slide we learned. Time them up, right? So we get the probability, it should be 1 times 364, 365 times 363, 365 until 366 minus n divided by 365, right? And what's the probability that we find at least 2 persons have the same birthday? 1 minus this, right? Straightforward. Here we need to know when n larger or equals 366, it equals 0, right? If we have a 366 person, we must find at least 1 pair, right? Okay, so that's the math. Then we plug in when n equals 10, we get it's 11.7. When n equals 20, it's 41.1. When n equals 30, it's 70.6. And when it's 50, it's 97. I know you guys still don't believe me. Okay, let's count how many people inside. 6, 10, 14, 15, 20, 25, 30, 36, 40, 43, 47, 49, 52, 54, 58, 61, 63, 65 people. Now we have 65 people in this lecture room, excluding myself. Who was born in January? January 1, 2, 3, 4, 5, 6, 7. 6. 27. 6. 21. 4th. 23rd. One more. 4th. Who is the 4th? Did I say the 4th? No? Okay. February. February. 1. Only 1. Okay, February. 1. February 5. Okay. That's the 1. March. 1, 2, 3, 4, 5. Okay. Which day? 23rd. One more degree. 18. 12. 11. Okay. April. So far we only get 13 people. So be patient. April. April. 1, 2, 3. Are you April? 3. Okay. 5th. 4th. 5th. Right? 5th. And 5th. Okay, welcome. Okay, May. 1, 2, 3, 4, 5. May. Which day? May. I saw one. Can you raise your hand one more time for May? 1, 2, 3, 4, 5. Okay, so what's this? 20. 20. 10. 26. Okay. So we get then we go to June. June. 1, 2, 3, 4, 5. Okay, so which day? 5th, 6th, 9, 23rd. One more. 2nd. Okay. I think a lot of people were born in November. July. 1, 2, 3, 4, 5, 6. Okay, which day? 16. 6. 1st. 15. Okay. So, like August. 1, 2, 3, 4, 5. Okay. 23rd. Okay. 26. 3rd. 16. Okay. September is more close to November now. September 1, 2, 3, 4, 5, 6. 24. 16. 15. So you are 60. This is 50. 25. 10. 23. Okay. So one more. 30. Okay. October. 1, 2, 3. 1. Are you October? Okay. 1, 2, 3, 4, Okay. Fifth, second, 11, 20. Third. 23rd, okay. Anyway, not this. November. Only 2, 3. Okay. Here. 8, 9. One more. 22nd. Let's count. 7, 13, 22, 30, 42, 42, 50. We get 67. So, how many people in December? 1, 2, 3, 4, 5, 6, 7, 8, 9. Which day? 12. Which day? 30. Oh. Oh, you have December? December. Both are December. Same day, 30. Okay. We can continue. This part, who is in December? 13, 31, 35, 34, third, second. Okay, so we get 3 pairs. The 5th of March, 20th of May, 30th of December. Now you guys get convinced. Last semester, we get 53 people, and we found 3 persons on the same day, and another pair on the same day. Okay, let's have 10 minutes break, then we will come back to the distribution, have a geometric distribution.
我大概现在有200个数据，然后我们可以从中间抽50个男的，50个女的，然后做compare。
总共是200个。
对。
这个也不算太大。
那一般这个总共数据要大概多少算？
一般的话，如果是几万，这样的话你抽的话，它才不受影响。因为你这个的话，它是你如果这样的话，要是抽男抽女的话，这个可能会比较麻烦，因为你这个200个的话，这个不算大，但是基本上也可以算出来多少人的这个是吗？然后的话，然后你再一直抽到5个，然后看看他们这个人的话，你把那个证明是不是刚好他们的这个population rate，因为你200这个它是population rate，你希望你这个知道，然后的话就是看一下这里那个就是有其他的小辈，他们的话要是看你这个写码的话，跟你的这个比较其他的小辈跟你的这个，另外的话，你们做这个写码的时候，一定要给它调成这个 centimeter。你如果说是那个39，那个不是一个 standard。可以看一下，我记得要是新加坡男生的话是个9，有39。 你转成那个离女生的话我忘了。差别应该不大。
可以是跟另外一个地方。
就最好的话是你跟武汉的有问题，但你现在没有的话，用其他的一个参考吧。你比如说，我可以说是，我是不是可以说让这个警察局的人的让这个平均的险码的话比新加坡的人大，或者比这个小，不一定说是非得相同，或者说是相同，反正你就是可以比较两个不同的 population。你这个的话，这种办法的话，那你就说是拿骰子在这里。就说是你把这个200个编好号，编好号之后的话，你说骰子一次的话，让你觉得一个数目，那么的话，你就是3个骰子，就相当于6进制。6进制的话，那你就是3位数，可以变到多少？你知道这个吗？
知道。
对，你这样的话，你就相当于6进制，这个保证上是一个大概我的。
就如果说我们比如说把一个数据抢断，然后间隔几个数，给它编成号语是
不影响，这个的话是不是单的。
2018。
那你记得你这个6进制的话，然后它最小的话，因为你用骰子的话，它是你要111，这是最小的。所以说的话，你看你是不是让把它那个全部减去1，你骰子的话变成0到5，这样的话可能会省力的。你变成0到5的话，那每个出现0的时候，你就0到5，因为后面有些大的数才会引导。然后这样的话，刚好你们3个人每人扔一点。
行
吧。
就是如果说一般如果说大的数字里面抽 group 的话，一般是几千几万个会比较好。
对。因为那小的话，你们sample的人数比较大。
I want to ask why the first person is 365 out of 365.
The first person, this is the probability that the nth person do not share his birthday. For the first one.
Oh, do not share his birthday.
Yeah. Nobody to share, right?
Why is it 365? Like, this one is the first person out of the nth person.
The first person only.
Yeah.
No others.
Yeah.
Just the first person.
Or just the first person,
Yeah.
not with the second.
No.
Oh, I see. Okay. Okay. Thank you, bro.
Welcome. Okay, so let's put it this way. Yeah, so actually this is the record is the content, and we can put it this way, so we know that is the
for 12, 13, 14, 15, and 16, these five are good horse. And you can see what is the ratio that the one occupy inside this five horse. The ratio. Yeah, so for example, the total, your total 50, and one can be but on average, if we assume that equal is average, then it should be 5/19. We go with 5/17/18. We can see equal this form is significantly below the average. Now you are not testing the population, you are testing the ratio. Given the ratio, we will calculate the functional ratio and do the possible testing. And this time, the average is minimum that is on this parameter. Yours? No. So basically, you just answer the same question, so which one you are prefer. And right now, we have a 1, 2, 16, 17, and 18 rows. So equally, it should be. And this is the 5 horse and in 3. So if it's average horse get equal probability, the probability of this should be 5/18. And you can get your estimation from how many people want to stay in this and divide the total. Then you can get the comprehensive interval of this. Yeah, and then you can have to test. You can test if the P is larger than 5/18 or equal or smaller. Then you don't need to report the mean. You just report the fixed parameter. Yeah. This is the constant. So this one you do have something. The only thing that you miss is just mean. No mean. Okay, so this will be completely useful or proportional. I think you know
Okay, let's continue.
Ya, Uma, sudah sudah dikunci ya? Sabre.
Play the subtitle. It's so weird.
Ya, Uma, sudah sudah dikunci ya? Sabre.
Anybody use the PC can help me out? Thank you. Yeah, so this one for sure they have the subtitle. This is the one file. Anyone know Korean can translate on site? Volunteer? So you can see on the Mac they do have the subtitle, but for the Mac I cannot get the voice out.
Just use YouTube.
YouTube?
Yeah.
Oh, yeah, that's good idea. Thank you.
Yeah, we already searched what is it. You just Google my sexy girl train scene.
But it's just this part.
Yeah, correct.
It's, oh, you did. Okay, thanks. Oh, that's they are laughing. YouTube.
Yeah, YouTube. SASSY. Girl. Train scene. No, you continue typing.
Ah, Tracy.
That's R.
TSR.
R, no, TRAI. No.
Oh, Thank you.
The second one. one, the second one.
Second one.
Second one.
The first one, the first one.
Oh, okay. First one.
Yeah, hang on. 야! 꼬마야, 지하철이 네 근처이야? 나 그래?
그녀가 집에 갈 때 전 부평역까지 데려다 줍니다. 남자로서 당연히 할 도리죠. 그동안에도 우린 재밌는 놀이를 합니다.
왼쪽 발로 공을 밟거나 넘어가면 내가 이긴 거고 오른쪽 발로 밟거나 넘어가면 네가 이긴 거야.
벌칙이 뭐야?
뽀뽀?
아이,
나 죽을래?
누가 정해?
때리기로 하자.
못 때리기야?
야 이기면 되잖아.
알았어.
야 이거 좀 불공평한 거 같아. 난 여자니까 따기로 하네.
근데 난 따로 할 거야.
난 여자잖아.
남녀는 평등한 거야.
좋아 그럼. 너도 따기, 나도 따기. 너 대신에 여자로 봐주면 죽어. 너 꼭 나를 따기 때려. 따기 안 때리고 나한테 물자라.
알았어. 너 따기. 남은 사람.
봐봐. 그게 더 공평한 거지? 어때? 내가 하는 거 같지? 같지?
나는 갖고 있었잖아. 그리고 이쪽에서 온다고 몰랐잖아. 이쪽에서 하는 건지 알았잖아.
몰라. 야 온다.
어이씨.
너 하늘이 왜 파란 줄 알아?
그냥 저 햇빛이 공기 중에 난반사돼서 흐르니까.
틀렸어. 나를 위해서야. 내가 하늘을 파랗게 원하니까 파란 거야. 알겠어? 너 불이 왜 뜨거운 줄 알아? 나를 위해서야. 내가 불은 뜨겁기를 원하니까 뜨거운 거야. 너 한국에 봄, 여름, 가을, 겨울이 있는 이유가 뭔 줄 알아?
너를 위해서.
네가 태어난 이유가 뭔 줄 알아? 나를 위해서야.
야, 내가 먼저 태어났는데 어떻게 너를 위해서 태어날 수가 있냐?
너 예배한단 말도 모르니? 예수님 탄생을 대비하기 위해서 베드로가 먼저 왔다. 몰라?
알지.
그러니까 돼. 똑바로 돼.
그녀와 같이 있으면 하루가 어떻게 갔는지 모를 지경이랍니다.
Okay. Thank you for the help to get this video done. I really want to show this video and some other videos, but never success. So this is a very good example for binomial distribution. So we learned the binomial distribution a few weeks ago. Here I just recap the key point. So for the binomial distribution, basically, first it should be Bernoulli trial. And first it should be Bernoulli trial. So we should have an nth Bernoulli trial. Then for each trial, they are independent. And each trial has the same successful probability. So from the video, we can know if a person crosses his left leg first, crosses that line first, the girl win. If he crosses his right leg first, the boys win, right? So the probability that the boys or the girls win is same, right? Normal case, we don't consider the army. Well, I will talk about that later. So for a random variable, for a random person, it either crosses the line by his left leg or the right leg, and the probability is 50-50. So each trial is independent. The first person and the second person, we cannot predict. And each trial has the same successful probability. So for each person, they all 50-50, right? Then we come back to army. For the army, can we consider this as a random variable? No, because if the first one crosses the line by his left leg first, then the following will cross the same, right? So when we do the survey, must be choose a random sample. You cannot just choose your friends, your good friend, and your relatives. It must be random. Okay, so for this one, the number of trials is n, and the successful probability is p. And we write binomial distribution as random variable x satisfy binomial distribution with n trials, and the successful probability is p. Then we can see this is the most basic, the discrete random distribution. And we go through this, and we get this probability distribution function. Based on its probability distribution function, we can calculate the probability that the successful events x equals 1, 2, 3, or any meaningful number. And here, we just go to, when this is larger, we can approximate binomial distribution to normal distribution. And when you do this, you need to get the boundary correct. Then we can see, we look at some special case. The Poisson distribution. In the binomial distribution, we have two parameters. One is the number of trials. The other is the successful probability, n and p. And we can see for this mu x, it equals the product of n times p. And for the variance, it equals the product times 1 minus p. If p is very small compared to 1, we can approximate 1 minus p equals 1, right? When p is small. For example, if p is 0.000001, definitely we can see this is equals 1, right? If this is the case, we get the average equals np. The variance equals np. We just need one parameter, the product of the number 12 to its successful probability. We just need this one parameter, and we can describe this distribution. So when the p is very small, we can approximate this. So we look at two examples. One distribution 1, this equals 10,000, and this is equals very small. And we can get the average is this, the variance is this. And for this one, the number of trials are different. This is 2 times more, and the successful probability is 2 times smaller. So we still get the same average and the same variance. So in this case, we can simplify the description from two parameters to one parameters. So we can just focus on the product of NP, the value of NP. This is enough to determine the distribution. So normally, when the number of trials is larger than 30, successful probability smaller than 0.05, and we can denote this as the Poisson distribution. For the Poisson distribution, they have one parameter, that's lambda. And this lambda equals the number of trials in binomial distribution times successful probability in binomial distribution. So if you want to apply Poisson distribution, you need to identify the distribution satisfy binomial distribution first. We cannot jump to the Poisson distribution directly, okay? Unless the distribution is given, they said the random variable satisfy Poisson distribution. Otherwise, you need to make a judgment if this satisfies binomial distribution first. If it satisfies binomial distribution, then you need to think about, do I need to approximate binomial distribution to normal distribution, or I need to approximate binomial distribution to Poisson distribution? This is the two different paths. Okay, so let's look at the probability density distribution function. And for the Poisson distribution, we just need one parameter, it's lambda here. And for the possible value, it could be 0, 1, 2, and this time it can go to infinity. It will not stop at n. It can go to infinity. And for any non-integer, the probability equals 0. So we can see this is the lambda equals 1, and this is lambda equals 10. And we can see this roughly, it looks like a binomial distribution. The Poisson distribution is only a special case for the binomial distribution. If one problem, you can solve it by Poisson distribution, you definitely can solve it by binomial distribution. Okay. And here, lambda must be a positive constant. Why? Can we get a negative n? Can we get a negative p? Then the product of them must be positive, right? Okay, so this example is very straightforward. It's given that the random variable satisfies Poisson distribution. Then calculate P0, P2, P10. So we just get the formula, then plug in the value, and get the answer. Get the formula, plug in value, answer, right? Do I need to go through this step by step? No. Okay. So then, just a quick question. How about a p minus 1 and a p 0.5? What's the value for p minus 1? 0, right? For all other values, it comes to this category. And the p minus 1 equals 0. P 0.5 equals 0. And if x satisfies Poisson distribution, then we can see its mean and variance are given by this. And here, we can also approximate Poisson distribution to normal distribution. And when we approximate Poisson distribution to normal distribution, then we don't need to do the continuity correction. It's just that this correction is very small. It's no bother to do it. But in the binomial distribution, you must do it. For the Poisson distribution, you don't need to. Then we can look at this example. So first sentence, they told us the number of hits in our satisfy the number of hits follows a Poisson distribution. So if we put a random variable x as the number of hit, then we know it satisfies the Poisson distribution. Then for the Poisson distribution, we need to get the parameter lambda, right? So in this way, they said the average in 1 hour is 27. And they ask the probability that there will be 90 or more hits in 3 hours. In 3 hours, not in 1 hour. So if in 3 hours, on average, how many hits do we have? 27 times 3, right, is 81. So then we can know that it satisfies Poisson distribution with the parameter 81. So we can just stop here. Any questions? 1 hour is 21. No, 27. Right? And 3 hours on average is 81. And because the average equals lambda, so we can get the average equals lambda. The lambda equals 81. So if we just get this Poisson distribution, and we can get this probability distribution function, right? And they ask the probability that the number of hits larger than 90, right? So we can just get 1 minus the probability x equals 0, 1, 2, 3, 4, up to 81. Then this is the probability larger or equals than 90. This is the right approach. Okay, this is nothing wrong. The only drawback is this will be very tedious. You need to calculate 90 items here. If you are on Saturday and Sunday, nothing to do, you can just calculate it one by one. But if you are on the exam hall, do you have the mode to calculate 90 items? No. You want to get the answer very quick, right? Then we check the criteria. And this one, it satisfies the criteria, and we can approximate this to normal distribution. When we approximate this to normal distribution, do remember that we need to get the same average and the same variance. So in the normal distribution, the average is 81, variance is 81, right? So basically, we convert the question from the discrete random variable to continuous random variable by keeping the same average and the same variance. After we get this one, then we can calculate the z-score, and you already do this a million times, and found the probability that larger than 90 is this part, and look at the z-table, you get when z equals 1.00, you get the area is 0.8413, and because they ask larger, so we look at the other side, it's 1 minus this, get 0.1587. Any questions? Okay, then we move to the hypergeometric distribution. So this is in lecture 5, hypergeometric distribution. Go to lecture 5. So in previous, when we talk about a binomial distribution, one criteria is for each trial, they have the same successful probability. For each trial, the value of P is the same, right? When this condition not satisfied, we need to use the hypergeometric distribution. Give you one example. Now, I have these two, laser pointer and a cell phone on the table. And I randomly choose one. What's the successful probability that I pick up a cell phone? Assume I'm numb, cannot tell it from shape. What's the probability I grab a cell phone? 100? 0? 50? 50, right? So the first, in this case, is 50. Now, I just grab one and put it on the chair. I grab another time. The second one, I didn't put it back. The second one, what's the probability that I grab my cell phone? 0, 50, 100? Which one? It depends, right? If the first time I grab my cell phone, then the second one is 0. If the first time I grab my laser pointer, then the second time it will be 100, right? So in this case, you can see the successful probability is not a constant anymore. It depends on the output in previous trials. If this is the case, we need to use the hypergeometric distribution. From now on, you cannot assume all the discrete distribution are binomial distribution. You need to check if it's a Bernoulli trial. If we have the same successful probability for all the trials. If they are, then go to binomial distribution. If not, go to the hypergeometric distribution. So then you need to know, normally we get a finite population contain n items. So this is the population size, not a sample size. This is the population size. When we get a small population, then the successful probability will be affected. So normally, if you see a population size is less than 50, you need to be alert. And you can look at the example, the tutorial question 1. They said we have a large shape. In that case, we can consider it as infinity. But if the population size is finite, it's small, then you need to think about the hypergeometric, if the hypergeometric distribution should be used. And R are classified as a success, and N minus R are classified as a failure. So basically, R is the number of my cell phone. If I have a lot of cell phone, for example, 3 or 4, and 3, 4 laser pointer, then we can get the R is the number of my cell phone, N minus R is my number of my laser point. So assume N, this is small case N. Small case N are sampled from this population. This N is the sample size. This log case N is the sample size. This capital N is the population size. And then we can see the X is a successful trial, has a hypergeometric distribution with the parameter capital N, capital R, lowercase n, and it can be denoted by this X satisfy hypergeometric distribution with the parameter capital N, capital R, and log n. Capital N and log n mean different things. One is population size, while the other is the sample size. Do you still remember this symbol? We talked about this about 1 hour ago, right? Whenever you saw this, replace it by the factorial of this divided by factorial of this, and the factorial this minus this, right? For this one, you need to calculate the value here first, then plug in the formula. Okay? And then for this hypergeometric distribution, this is its probability mass function, and this is the mean, and this is its variance. Again, this time you can see they get a bar here. This is not equals to factorial. This is just the value. Okay, this is a factorial. This is just its value r divided by n, and this is just a value 1 minus r divided by n. Okay? Any questions? No? Then we go to tutorial question 1, 2, 3, 4 in tutorial 2. So if you cannot see it clearly, please move forward. If I zoom in further, you can only see part of this. Okay, so for the first question, a distributor receives a large shipment of components. The distributor would like to accept the shipment if 10% or fewer of the components are defective, and to return it if more than 10% components are defective. He decided to sample 10 components and return the shipment if more than one of the 10 is defective. So this is the question. We get the shipment and the component, some of them works, some of them don't. So if you are the engineer and you want to make sure that this shipment has the defective component less than 10%, and the approach that the distributor uses is sample 10 components out. If he found one is defective, then he rejects this. More than one, he rejects this. Then we can look at the first line. They said a large shipment. What does this mean? That means the population size is very large, right? a large shipment, it may include thousand components, right? So when we take one out, it doesn't affect the rest. Then we can see the part A, if the proportion of defective in the batch is in fact 10%. I don't know why I need to write. Okay, here. So in this shipment, the defect rate actually equals 10%. Then we can see the approach that P, if we choose one component out, what is the probability that this component is defective? .1, right? If I take the second component out, what's the probability that the second one is defective? Same. Third one, same. So then for each trial, we can get either it's defective or non-defective. This is the binary trial. Then for each trial, they are independent to each other. And for all the trials, they have the same successful probability, 0.1. In this case, we know that X, random variable X, the number of defective components satisfy binomial distribution, right? And how many trials the distributor did? 1, 2, 1,000? How many? 10. So the number of trials is 10. And what's the successful probability? 0.1, right? So we know X satisfies binomial distribution with the number of trials is 10, successful probability is 0.1. So then they ask the probability that X larger than 1, right? Then you can get it equals P X equals 2 plus P X equals 3 up to P X equals 10, right? So this is the direct approach. Or it equals 1 minus P X equals 0 plus P X equals 1. Either way are correct. And for P X equals 0, we know it equals, the formula is n factorial divided by x factorial n minus x factorial P X 1 minus P up to n minus x. And n equals 10, x equals 0, P equals 0.1, 1 minus 0.1, 10 minus 0, right? Then you can get the value, right? Okay? Then we can look at the question part B. Part B, they said the defect rate is actually 20%. Now the defect rate is 20%. So if we choose the component randomly, X still satisfies binomial distribution. And what's the number of trials, the number of components that the distributor should choose? It's unknown, right? That's they ask the sample size, so it's n. And what's the successful probability for each trial for part B? 0.1, 0.2, 0.3, 0.2, right? So we get it equals 0.2. Then they said they want to have the probability no greater than 0.1 if none of this. So we calculate this one. We plug in when x equals 0. Then we get n factorial divided by 0 factorial, n factorial, and then p 0, and 1 minus p n minus 0. N factorial will cancel to each other, right? 0 factorial equals 1. And then p power 0 is 1. So we only get 1 minus p to nth power left when x equals 0, right? So we get the p x equals 0 equals 1 minus p up to nth power equals 1 minus 0.2 up to nth power. This probability is smaller or equals than 0.01. Okay, so this one, can you solve it to get n? We get n is larger or equals 20.64 because the sample size is integer, so we should take 21 or 20. Exactly. Any questions? No? Then we can look at question 2. So for question 2, we can see we have 3 diodes, and each diode has a probability p equals 0.002 of failing. The first one is asked what's the probability that exactly 2 diodes fail. One circuit board contains 300 diodes. So what's the probability that 2 out of 300 fails? So when we choose the first diode, what is the probability that this diode fails? .002, right? For the second diode, what's the probability that it fails? Same, right? The third one, still same. So basically, this is satisfied binomial distribution. And what's the value of n? 300. And what's the value of p? 0.002, right? Then we can get is a satisfied binomial distribution, and you can plug in and get the probability x equals 2, and the average, and also the standard deviation. And in the part D, they ask the probability that none of doubt fails, right? So for this one, basically x equals 0, and you can get the value is 0.5485. For the part A, B, C, D, can I use the Poisson distribution? Can, right? Because n is larger than 30, and p is smaller than 0.05. So for A, B, C, D, we can use the Poisson distribution. How about E, part E? For part E, they ask 5 boards are shipped to a customer. What's the probability that 4 or more of them work? If we want to get a diode works, if we want to get the circuit board works, all the diode must work. So when we choose one circular board, what's the probability that this circular board works? 0.5485, right? Choose the first one, the probability is 0.5485. Choose the second board, what is the probability that the second board works? Still same. What is the probability that the third board works? Same. So it satisfies binomial distribution. And this time, the binomial distribution has a parameter. The number of trials is 5. The successful probability is 0.5485. For this binomial distribution, can we approximate to Poisson distribution? No, because the number of trials is small, and the successful probability is too large. Okay? Then we look at question 3. For the question 3, grandma want to make a bread. And for the rinsing bread, it includes 3 loaves, and each loaf contains 20 slices. So how many slices do we have? 60, right? And they ask, we randomly choose one slice. What is the probability that this slice contains no rinsings? So for this one, you need to think about here, we get 60 slices. Then we put 1 rinsings randomly. What is the probability that 1 slice receive this rinsing, the first rinsing? 1/60, right? We put the second rinsing. What is the probability that this slice receives this rinsing? 1/60. So grandma just keep doing this and repeat 100 times. So she put 100 rinsings into this batch. So we can see if X is the rinsings in the randomly choose slice, X should satisfy normal distribution, should satisfy binomial distribution. Satisfy this binomial distribution. and the number of trials is 100, and the successful probability is 1/60. And we can see, because the number of trials is larger than 30, the probability is smaller than 0.5, so we can approximate this to Poisson distribution. How to get the value of lambda? N times P, right? We get this. So then you just similarly, you can get the rest. For the question 5, just half a minute to explain question 5 for question 4. For the question 4, you can see the question 1, the shipment is large. And for the question 4, the shipment only contains 40 atoms. When it's 40 atoms, this is the population size. You need to be alert. In this case, we should use a hypergeometric distribution, not a binomial distribution. Then, basically, you just find out the value. These 5 defect items. So this is the value of R. You can calculate this value of capital N, value of R, and they choose how many they choose. Oh, sorry, they choose 5. This is R, and also this is log case N. 5 items, so this is sample size, and in these 40 items, 5 of them are defective. So basically, the capital R also equals 5. Then you just plug in the formula, get the answer. Just be alert that question 4, you should use a hypergeometric distribution instead of a binomial distribution, because the population size is small. Okay, any questions? If no, that's all. And thank you for coming. Next week, Mr. Raymond will conduct the lecture. And next week, I will do the tutorial for the tutorial 4. Okay, see you next week.
How to know when we use binomial and Poisson?
Binomial or Poisson?
Yeah.
So when it's whenever you can use the Poisson, you can always use the binomial.
Oh, so basically, the problem is binomial.